All right, so we defined, we said two statements are logically equivalent if they have identically the same truth tables. So we're going to use that concept to prove a couple of these logical equivalencies. One of De Morgan's laws says the negation of an or statement. So for example, it is not the case that P or Q, that's equivalent to not P and not Q. So when you negate an or statement, you might actually end up with, when you distribute the negation, you get an and statement, and vice versa. Okay? So we want to prove this equivalence. We have two individual statements. So my truth table, I'll have P and Q. Okay? And then I need, let's do P or Q. Okay? So P or Q is true if I have exactly, well, I have at least one true. So it's true, 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 false. Okay? Then I'm going to do the negation. So it's not the case that P or Q. And I would have the exact opposite truth table. I just flip all these. If this is true, then this is false, 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 true. Okay? So that's one of the truth tables I need. And now I need not P and not Q. Maybe I should have had two more columns for not P and not Q. Or I can just do it over here. I mean, it doesn't always said you have to do them in a certain order, but that would have been nice. I guess not P would therefore be false, false, true, true. Not Q would be false, true, false, true. And then not P and not Q. So for this statement to be true, I need both of these two columns to have true. That only happens in the fourth row, right? Not P, not Q. So only in the fourth row is there true, so the rest would be false, false, false. Looks familiar. So this is equivalent. These statements are equal. They're logically equivalent because their truth tables are identical. And like, some say, like, how can you? I mean, what else do you need to do or say? I mean, this is fine. If you just kind of circle these two. If you wanted to write a sentence, you say, they're logically equivalent because their truth tables are identical. That's fine. So this is what I mean. It can't just be the fact that they both have 3 F's and 1 T. I mean, it has to be the same exact identical row for row. So false, 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 true. Question?
Do you want us on our homework to draw out every single column, or if I just know that not P, I just do that in my head?
Okay, so maybe these rows you wouldn't do.
Yeah, is that all right?
I mean, I guess. I mean, you get more used to it. Here, we're doing at the beginning. It might be good to include these. If you start showing too little work, maybe I'll make the statements a lot more complicated with that. I mean, I know it doesn't take that long really to do this. Now, I try not to assign too many where you have like eight lines. I didn't assign any that had 16 lines. Did I? Like P or not Q implies R or R and not S. That'd be a good one. 16 lines. Or T, 32 lines. Yeah, let's not do that. So, okay. So that's De Morgan's law. The other De Morgan's law where you start out with an and statement here, the negation of P and Q equals not P or not Q. I mean, it works, very similar. All right. Another one I want to choose, one of the distributive laws. Okay, so here's one of the 3 statements. So P and Q or R. Okay, so think about that. So we have P and Q or R. So when would a statement like that be true? An AND statement is true if both of these are true. So P has to be true, but for a Q or R to be true, only one of them has to be true, right? So this, you can think of this, I'm telling you it's equal to P and Q or, right, P and R. So does that make sense? If I said P and Q or R is a true statement, that's the same as saying that P is true and Q is true, or P is true and R is true.
That also means that they both could be true, right?
Right. Or they could be both, or both could be true. Correct. One or the other, or both. Okay. All right. So let's look at. So I'm gonna need 8 rows here. Right. So true, 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 false, 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 false. Q is gonna be true, true, false, false, true, true, false, false. R is going to be true, false, true, false, true, false, true, false. All right, so I'm going to use, I need a Q or R column. So Q or R, I'd get a true if I have at least one true in these rows. So the Q and R. So true, true is true, true, false, true, false, true, true, false, false, that's false, true, 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 false, true, false, true, true, false, false, false. Any questions about that? All right. Then I need a row or a column for P and. Let's do P and Q or R. Okay. So the first statement. Yeah, we do that way. I'm gonna say maybe we should do columns for P and Q, and then a column for P and R, and then maybe put our last two statements that we're trying to show equivalent right next to each other. Would that look nicer? Is it more correct? I don't know. No. So let's do. What did I say? Q. Let's do P and Q, and then I'll do P and R. So I have all the three, pieces, and then I'll do P and Q or R, and then I'll do P and Q or P and R, and then it looked kind of nice because like the last two columns should be identical, right? Mm-hmm. And that would be a nice way to present your findings here. All right, so P and Q, we need both P and Q to be true, to get a true. So first, true, 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 false, false. And then false. Oh, the last four rows are all falses on P. So the rest of this has to be. I need to get my rows lined up. You have to get lined paper, don't you? Okay. So what's that? True, true, false, false, and then since P is false, the last four rows are false, 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 false. P and R. Okay, so I have true, 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 false, true, 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 false. And again, the last four rows of P are false, so P and R, the last four rows are all false. All right. So let's do P and Q or R. So P and then and Q or R. All right. So I got true, 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 false. That's false. And then, again, since P is false on all 4 rows, the last 4 rows, I know that these have to be false, 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 false. Okay, so that's what we're looking for in this last column. All right, so now I'm looking at these 2 columns. I need to have at least one true for P and Q, or P and R to be true. So I have true, false, that's true, false, true, that's true, and then the rest are all falses. Looks identical to me. Okay. So, so saying that, so now you can interchange these statements. If you have it's saying P and Q or P and R, that's the same saying P and Q or R.
So later on, if we were to use this, would we refer to this as distributive 1, or we use this as like rule 5?
I'm not going to refer to them by number. I mean, the reason why we're practicing showing the statements are equivalent is because later when we prove statements, it'll be often easier to prove an equivalent statement. So, we're just getting practice. We're probably not going to use this in a proof. So I'm not going to we're probably not going to be a need to refer back to this. But it is useful to know that if you distribute an and statement, you get it's just like the regular distributive law. And the same thing for OR. The negations will come in. We'll need the negations probably more than these type of statements. Because I showed you an example where the contrapositive is equivalent to the if-then statement. So, but it involves negations. Okay. So I don't think I can't say for sure, but I don't think we'll ever have to refer back to this particular thing. And I probably won't ever say, well, yes, according to De Morgan's law, we have to. But I mean, I might. We just need. I usually don't call by name. I would say, well, the negation of an and statement isn't or. The negation of an or statement is an and statement. Or you kind of toggle back and forth when you negate. Okay. Any other questions? So, you guys, I already told you your homework from 2.6, right? So, maybe you've already finished it. I don't know. So, I guess you guys any other questions about truth tables? Okay, so 2.6 done. Let's do talk about 2.7. Okay, so some sentences that we've talked about so far, where we haven't. There's some statements that occur in mathematics that we haven't developed enough symbols to rewrite these statements in symbolic logic. So we're going to kind of fill in the gaps with these symbols called quantifiers. Okay, so that's section 2.7. Quantifiers. Okay, I mean they're called quantifiers. I mean you got the word quantity, kind of the same prefix there. So these are symbols that refer to a quantity. There's a lot of statements in mathematics that refer to quantities, like something is true for all integers. And so you're saying something that's universal about every integer. Or you say every integer is even or odd. So I'm saying a statement about everything, all integers. Sometimes you just say talk about some, or like some integers are even, some integers are prime. So that refers to a quantity. I mentioned this the other day. Some, when you say some, if you had a homework problem that said like some sets are finite, that just means at least one set is finite. So we're talking about there does exist a set that's finite. Okay, so those are sentences that occur a lot in math theorems. Okay, and so I'm going to show you the symbols for those statements. Okay, so the phrases there is, there exists, phrase for all, and for every. These phrases, and it's slight variations, like just the word all, just the word every, or sometimes the word some instead of there is, or there exists. Sometimes you say some. So there's variations of these. These phrases occur frequently. They appear frequently in math theorems. Okay, so for these statements, we need these quantifiers to help us break down these statements in symbolic logic, and so then we can apply our knowledge of, like, for example, Morgan's laws. Like, what if you negate a statement that says a quantifier? So we'll look at that a little bit later. But okay, so here's an example. Two examples. There is an integer that is even and prime. Okay. So you'll see we're going to do some translations. We'll have statements and we'll translate them into symbols, and then we'll have symbols and we'll try to translate them back into phrases. And mathematicians can get kind of specific and kind of use English in a kind of weird way. Instead of saying there is an integer that is even and prime, a more kind of standard way, like if you're just sitting around talking, you would probably say something like, some integers are even and prime. That's probably maybe more, let's say less math speak kind of way. But we say these sentences all the time. There is an integer that is even and prime, or something. Or you could say there exists an integer that is even and prime. I mean, you probably don't talk like that, right? Is there any milk in the fridge? There exists some milk in the fridge. It's like, no, there's some milk in the fridge. It's just, but mathematicians might, logically those are equivalent. But it's like, yeah, that's annoying. So, all right, so. There is an integer that is even and prime. So what I'm getting at is when you see the symbols, you'll try to translate that back to an English phrase, and it might come out like a robot speaking instead of like. So it kind of would be better if you could even translate it to like a more normal phrase. But I'm not going to say this is wrong, even though it might not be exactly the way we speak. Okay. So think about that. Here's another one. How about every natural number is positive. I mean, that's a statement about all natural numbers. Now, the first statement, these are actually both true statements, by the way, right? There is an integer that is even and prime. Even if I said some integers are even and prime, those are both true statements. It's true because I can find at least one, the number 2, is both even and prime. Every natural number is positive. Well, the natural numbers are 1, 2, 3, 4, 5. So yeah, they're all positive. Okay, but that's true for every single one of them. Okay, so we're going to look at how can we write these using symbols. We don't right now. Let's see. Well, we could probably write this one without quantifiers, and I'll show you how you can do that. But this one, I think you really need a quantifier that describes this phrase, there is or there exists. Okay? So here are the symbols. The quantifiers. I'm often curious, how these symbols come about, but we use it first. So a backwards capital E. So if you type up your homework, good luck finding these symbols on your.
They're somewhere in there.
Yeah, they are somewhere. I mean, I've used Microsoft Word. You can find these symbols. If you use other software for, you might have a harder time finding these. But anyways, so backwards E. This is the symbol that stands for those phrases there is, there exists, or some. Okay? This stands for there is, or there is a, there exists a, and then also the word some. Like I could have said, some integers are even and prime. Or there exists an integer that is even and prime. Or there is an integer that is even and prime. Okay?
But it's not for every for all.
It is not for all. It is another symbol for all. And it looks like this. So it's an upside down A. So I think they tried a backwards A for a while. It didn't work too well. So they went upside down. And I couldn't do an upside down capital E either, I guess, right? So upside down A stands for, this for all or for every. And there's other variations. I mean, you could just say the word all instead of for all, or like all, even all natural numbers are positive. Or every natural number is positive. So all or every. And again, this is where experience kind of comes in. When you see a symbols, you end up reading it with the all the little words that you need to make it a proper English sentence. Okay. So these are standard symbols. It's not just this author made up these symbols. I mean, mathematicians know what these mean. That's what they mean.
So do we still use any of our set builder symbols? Or any of this, or is that completely separate?
Set builder, like intersections
Like
and
elements
units.
and
Oh yeah, you combine all these. These are just more logic symbols. And so we'll have sentences that can use all those things. Element of. That's what you often see for every natural number, or every natural number. So that's how this is how I would write the word, how I would translate this, I would say every natural number. So for every element n of the natural numbers, I mean, you can try to translate it literally, like for every n that is an element of the natural numbers, I mean, that's how you would literally translate this. For every n that is an element of the natural numbers, well, why don't you just say every natural number? And that's more of a easier way to say this. So when you see this, you end up hopefully maybe at first you'll literally translate it word by word, but then you'll get the meaning of it. This means every natural number. Every natural number. If you have a sentence like every natural number is positive, we could like that. Well, let's do that. So every natural number is positive. I wrote that. So I would write for every n that's a natural number, or for every natural number n, and yeah, you could actually write it in words. N is positive, but there's even more math symbols that we have for saying something is positive. We mean it's greater than 0. Yeah, so you could even just say that's even more concise than actually using the word positive. Okay, because these mean the same thing. N is positive, N is greater than 0. Okay. So So this would be a way you can translate the phrase, every natural number is positive. Okay, any questions so far? How about, one more thing, I wanted to define, the names of these. When you say there exists, they call this the existential quantifier. So you'll see maybe not like what is the meaning of life quantifier. It's an existential, like existence. I mean, this is the existential quantifier. That's just what it's called. I guess it's just sounds more proper than the backwards capital E. Saying that all the time. We use the backwards capital E. You say, once you use the existential quantifier. Then the upside down capital A, that's called the universal quantifier. You can see why, I mean, because it talks about everything, the whole universe, every single natural number. If your universe is natural numbers, every natural number is positive. So we're saying something universal about all things that we're considering. Okay? So you might hear those words, universal quantifier, existential quantifier. All right. So basically, the rest of 2.7, I'm going to give you some examples of phrases, or sentence statements, rather, and how would you translate them using quantifiers. And then, kind of vice versa, I'll give you a statement in symbols. You could try to unravel it, rewrite it as an English sentence. Okay. So 2.7, the homework is actually translating logical symbols back into English.
So what we're actually getting to is where we can take a statement, turn it into our terms of P and Q, and then prove whether the statements are true or false with true-false statements.
Yeah, that's kind of the idea. I mean, to truly, sometimes to understand exactly what a statement is saying, because you maybe want to try to prove it. Well, if you can translate it to symbolic symbols, to symbolic logic, then you can use, like maybe you have a if-then statement, so that maybe you can rearrange it to make it a contrapositive type statement that's equivalent, and prove that. That might be easier somehow. Okay, so that's the idea, that maybe we would translate it into logic so you can really understand, make sure you're absolutely certain what the statement is saying, but also maybe you could translate it to logic. I mean, usually, this is not like a step you would do when you're proving statements, but it could be something on the side you could do, just kind of to convince yourself you know exactly what the statement is saying. And now for this class, I mean, our statements are going to be pretty straightforward. We're often going to be, if-then statements. But it is definitely good to know these symbols. I mean, these are used all through mathematics. Above this class, I mean, you can use, you might see these type of symbols. Any of you take, what do you call it? Is it real analysis 1 or analysis 1? What do they call it?
Just call it analysis.
Analysis. I mean, should see these all the time. Has anybody taken that yet? Or taken it now? Or?
I think this class is
It's correct for that. That's why. I mean, you use these symbols all the time. You use them on every problem you do when you're writing delta epsilon proofs of limits and things. I mean, you use them all the time. So, all right. Oh, I had another sentence on the board, right? Yes. Sorry. There is an integer that is even and prime. Okay, so there is, you're thinking that's, that big backwards capital E, the existential quantifier. So there is an integer, okay? So usually, oftentimes you use n. It doesn't have to be the letter n. It can be x. But you can say there's an element of the element of the integers. Okay, so I'll probably write it like this. So there exists an n that's an element of the integers. And you could literally translate that like that, but more likely you would translate it as there is an integer. There is an integer n. Okay? Such that, you just kind of your comma, and then what about n? Well, n is even, and n is prime. So it's an and statement. Okay? N is even, and n is prime. So one thing I did want to mention, well, any questions first about this? The use of the...
Could you just write n equals 2?
Well, that's equivalent to what I said, but, well, no, you're proving, that's not saying that, so n equals 2, that's an open statement. But this is a open sentence. But this makes you think of the number 2, right? The number 2 proves that this is a true statement, but saying there's an integer called 2, that's not really the same as this.
Could you say
statement.
For every number, or for every n, it's an element of z, it would be n equals 2? Or is that just not?
So you're saying every integer equals 2?
No. Yeah,
Yeah,
see,
you know
that's
what I'm saying?
simple.
So you'd have to say
Yeah.
there is an integer, there exists an integer n such that n is even and n is prime. I mean, that's how you would translate that literally. But now I know, I mean, the reason why this is a true statement is because the number 2 does exist out there. So if I said prove this statement, you would say, well, the number 2. The number 2 is even, and the number 2 is prime. The number 2 is an integer, so therefore this is a true statement. Okay. So some of these statements, just to get some statements, they might not even necessarily be true. I mean, these 2 statements were true so far. But I can just write some sentences that we can translate, and they're not necessarily even true. Okay. So, how about this sentence? Some integers are not prime. Some integers are not prime. So the word some, we're not talking about every integer here, we're just talking about some of them, so that's the same existential quantifier. Some integers are not prime. So what we're saying is, one way literally, there exists an integer n such that what? How can I write the condition here for n?
The negation.
And is not it.
Yeah. If you use, there's the word not there, so they kind of want you to use that negation symbol. So it is not the case that, what? N is prime. I mean, you could have written such that n is not prime, but they kind of, when they say that, when they use the word not, I think they would want you to, it's like a homework problem, they want you to kind of use that negation symbol.
Is there a reason why we're using a comma now for such that rather than a colon?
Yes, because we're not using, this is not set notation. It's just it's kind of like, you'll get used to this as just, it's almost like you can, in mathematics, you can use real words, like real English words, and then you can throw in these symbols, and you just kind of mix and match oftentimes when you start writing your proofs. And so this is like a sentence. So a sentence, grammatically, a colon means something different, right? It kind of means like stop here, and then like you're giving like a clarification of something you said here. And so, yeah, now we use a comma. That's a good point to note that, it's like we're writing a sentence here, we're just writing in a different language. And this is really a new language, symbolic language. Okay. Yeah, so we would use commas here. And so you could read this literally, there exists an n, which is an element of integers, such that it is not the case that n is prime. That would be a literal translation. But that's not really, the idea of when I say translate this back to English. You could do a literal translation, that's fine. But what are you trying to get at here? You're trying to say that, okay, some integers, or there exists an integer that is not prime. There exists an integer that's not prime. That might be a more common way to translate this. There exists an integer that is not prime. Or there is an integer that is not prime. Or some integers are not prime. It's even, kind of be better. So there's more than one correct way to translate this back to English, right? Some of them are more normal sounding uses of English. Any other questions? Right here. The square of every real number is non-negative. Is this true or false?
False.
The square of every real number. So I mean, you take that number and square it. So you take a number, take any real number, square it. Is that going to be non-negative?
Yeah.
Yes. So this is a true statement. The square of every real number is non-negative. So that's pretty normal sentence. I mean, it's a math sentence, but it doesn't start off with a every, but there is this every here. Okay. So we're using the universal quantifier here.
For every real number, the square is non-negative.
Okay. So for every,
Could you put n squared on the bottom?
well, this is a statement about every real number. So I would start off with
And is it only
for every real number. Okay, so you can often, it's not necessary, but it's common. X is used for a real number, an arbitrary real number. N is usually when you have a more discrete set like natural numbers or integers. It's not necessary. I mean, it's just common. N and M often are your arbitrary integers. X and Y are often the arbitrary real numbers. It's not more correct because I'm using nothing X. I'm just saying. Just want you guys to see, what's commonly done. Okay. So right here, this statement right here. This means for every real number X, okay, or for every real number. For every real number X, what is true about that X?
the square?
X squared, the square of X, greater than or equal to 0. Excellent. So for every real number X, X squared is greater than or equal to 0. So to translate that back to English, you maybe start off with for every X, there's an element of the real numbers. It is the case that X squared is greater than or equal to 0. And then you kind of think about what is the statement really saying? What we're really getting at is that the square of every real number is non-negative. I mean, you could say greater than or equal to 0 in your translation. But, okay. Any questions? Next. Every subset of the integers is finite. First of all, true or false? Every subset of the integers is finite.
False.
Say it's false? Why? Becky said it's finite. That's 0.
Well,
What does it mean?
One-
What it means for finite?
The integer is a
Less than an
subset of
infinite
itself,
number.
therefore it's an infinite
Ah.
set.
The integers is a subset of itself, and integers are not finite. Finite means it has finitely many elements. Is that what you're thinking?
yeah.
Yeah. So You can, I mean, there's actually an infinite number of subsets that have infinite order. So think about all the multiples of 2. That's an infinite set. All the multiples of 3. That's an infinite set. All the multiples of 4. That's an infinite set. I mean, but they're all subsets of integers. Okay. So are some infinities bigger than other infinities? Like, that's kind of weird, right? Like, the integers has infinite number of numbers, but they haven't. There's many sets that are an infinite number of sets that have infinitely many elements that are proper subsets of integers. All right. So I digress. Let's see. What is this? A backwards E or upside down A? Every, right? Every, all, some. Sorry. Every, for all. Those are your universal quantifiers. All right. So what are the objects we're talking about here? Making a statement about
Power.
subsets of the integers, right? So I'm not going to use a lowercase n from my arbitrary object. That would be like a number. An arbitrary set, what does sets look like? What do we use for sets? Right? Capital letters, right? So you could use capital X is kind of a common one we've used for sets. Capital A, I don't know, that kind of look weird, right? For every capital A, it's like, you could use that, I guess. Okay, so I'm going to use capital X, right, for an arbitrary subset. A set, but it's a subset. So how can I say that X is a subset of the integers?
The little C with the line.
So it's a subset of the integers. For every subset of the integers, that's kind of the way I would read that. So for every set X, that's a subset of the integers, how you would literally interpret that. What is true about that set X? So what is the definition of a set being finite? What do we know about its size? Less than infinity. So one way to do it is the size of X, when we put absolute value bars around X, is less than infinity. That's one way to say it. I mean, you could just use words. You could just say the size of, or you could just say X is finite. But it's kind of nice to use. It's all symbols.
Would we also include before 0 is less than X, less than infinity?
Not necessary. It's saying something that's finite, it could be 0, it could be 1, it could be 2, it could be any size other than infinite.
Oh, I was thinking natural numbers. I think that's why.
Oh, okay.
Would be equivalent to say it does not equal infinity.
That's true. Because, there's the only cases for sizes are the whole numbers. 0, 1, 2, 3, 4, 5, 6, 7, up to infinity. So yeah, so the only thing you eliminate would be infinity. Yeah, I think it's way fun. See that? I guess that's. Could you, would you think of that as the same as saying it's finite though? I think they're equivalent. You could say. I think I'd probably stick with that maybe.
I think
saying something that's finite is saying it's really less than infinity. Okay. Now you're true that they would be equivalent though. If the size doesn't equal infinity, it's forced to be less than infinity.
Would that one also be true if you said the negation of the absolute value equals infinity?
But that probably would be the easiest way to translate this into symbols, so that you know they'd be equivalent. Now I think I heard somebody say something about power set. Yeah? How could I write that using the power set notation?
I was just thinking of replacing the universal and the X, making a script P and then a symbol for integers inside of it.
Well, okay, so what I was thinking of, instead of saying that X is a subset of the integers like this.
X is an element of the power set.
So saying that X is a subset of Z is the same as saying that it's an element of the power set of Z. You see how those mean the same thing? X is a subset of the integers is the same as saying X is an element of the power set of the integers. Because the definition of a power set is it's a set containing all the subsets of Z. Okay, so I want to point that out. I don't typically use that notation for power sets. this seems easier to me. Like you have to know another definition to know this notation, but it is equivalent. And there's some examples in the book where they use that. They use the power set notation instead of just is a subset of. All right. Let's talk about combining quantifiers. Yes, I got one here. Okay. Sometimes, I mean, you can actually have two arbitrary things you're talking about. Like, if I said the sum of two integers is an integer, I would say something, you're saying something about two objects. You say for every x and for every y, x plus y is an integer or something. But really, so if you're using for every and for every back-to-back, or there exists and there exists, they're not, the order isn't that important. But I'm going to show you some examples where the order of makes a big difference here. Okay? All right. For every integer x, there is an integer y such that x plus y equals 0. So this statement has a every or for every, and it has a there is or there exists phrase. So we're actually going to combine, we're going to use both quantifiers. Okay? All right, for every integer x, how would you translate that? For every integer x.
Universal.
Sine x. Is that enough?
Element of integers.
Yeah, it's an element of integers. And here's the thing: if if say you're taking a number theory class where all you're talking about is integers, you oftentimes just forget it's an element of the integers statement. I mean, you might just say for every x there exists a y, but because maybe the whole semester all you've been talking about is integers, so it's implied that what the universe is. Okay, but it's not bad to include that. Okay, so for every x that's an element of the integers. Okay, so in other words, for every integer x, there is an integer y. There exists. There is an integer y, such that, and I have another comma probably, such that x plus y equals 0. Okay. Any questions? How about this? There is an integer y such that for every integer x, we have that x plus y equals 0. It's almost saying the same as the previous sentence, but let's translate this one. So now it's saying there is an integer x, there is an integer y first. It's saying that first, right? So there is an integer y such that for every integer x, so for every x integer, we have that x plus y equals 0. And that's where, you kind of supply your own, I don't need to say we have that. It's kind of like a such that, therefore, or so I want you to look at these two statements. only one of them's true. Which one's true and which one's false? What do you think about the first one? True or false? Let's take a look. True. False. Nobody? Okay, you're right. This is true. That one's false. Let's think about exactly what this is saying. For every integer x, okay, it's kind of like no matter what integer you give me, okay, give me an integer x. No matter what integer you give me, there exists a y. I can find a y so that the sum x plus y is 0.
So
Right?
one is like,
Somebody give me an integer. 2. Well, I can find negative 2. 2 plus negative 2 is 0. Okay? Alright, now look at the second sentence. There exists an integer y such that no matter what integer x you choose, x plus y equals 0. That's not true. It says that there's one y that no matter what other integer you add to it, you always get 0. It's not true.
Why couldn't you do the opposite? If my y is 2, then I can make my x negative.
It says that what this is saying is there's a y that works for every other integer.
because if we work this
It doesn't work that way. What it's saying is for every integer, no matter what integer you start with, I can find a one that will make the sum 0. But you can't find a y that works all the time. Remember, this y depends on what you chose first.
for every input, we have exactly one output.
Yeah, for every, it says for every integer x, there's an integer y to make this sum equal to 0. But this time it says there is an integer y that works all the time. There's an integer y such that you choose any other x and this sum will always equal 0. That's not the case.
Vertical and that's
So it really makes a difference the order. Okay? So this says basically for any integer you choose, there is a y. I can find a y to make this true. But you cannot find. It's not true that there's a y that works for every x. There's a different y that works for every different x. Yes.
For the second one, if you said there is an integer y for every integer x, would that change the meaning?
Well, yeah, it would kind of, right? Like, because you're saying like they're kind of paired up, like yeah, and that's kind of like what the first one is saying. For every x, there is a y, there is a pair that works, but yeah, you can't really take out that phrase such that, because that's why this is. I'm saying that's why this is wrong, is because you're saying this is implying that this y works for every other x, and that's not the case. Okay. Do another example here, combining. Okay. So assume we are talking about integers. Okay, so that way I don't have to keep saying is an element of the integers. Okay. All right. So I want to have symbolic logic over here. I want to have a translation over here. And let's say true false on the third column. True false. Well, what is an English translation of this symbolic sentence?
For every x, there is a y that, or such that x times y equals 0.
So for every x, there is a y such that x times y equals 0. Okay. So for every, I said we're talking about integers. When I say for every x, I really mean for every integer x. Right? For every x, there is a y such that x times y equals 0. Is that true or false? True? So for every x, there exists a y such that x times y equals 0. Okay. I agree. True. What if I change this? So there exists a y. Well, I shouldn't have said that. What if I change the order of the so how would you translate that? Yeah. There exists a y such that for every x, x times y equals 0. Okay. So there exists a y such that for every x, x times y equals 0. Now we're saying there's a y that works for every x. True or false? True. So in this case, either one, both these statements are true, and the reason is because even in the first sentence, 0 works for almost every integer. But if I started out with, if x was 0, then I could choose any other integer for y. But the second one, the number 0 works for every number, every integer, right? Like I could choose 0 for y, and no matter what x you give me, x times y is 0. And here, no matter what x I give, whatever integer I give you, I can find a y. There exists a y such that the product equals 0. Okay? If you start off with any integer other than 0, you better choose 0 for y. Right? But if you choose 0 for x, you can choose a million for y, and then 0 times a million will still be 0. Okay, so both these are true statements. How about this? How would you translate that? There's an x, okay, there exists an x, such that for every y, x is greater than y. Okay? So there is an x, or there exists an x, such that for every y, x is greater than y.
Doesn't it matter where you put the such that at?
Yeah, I mean, kind of has to flow. I mean, where would you like to put it?
Can you put it after the everyone?
There exists an x for every y, such that, yeah, I guess that'd be fine. Yeah. And oftentimes, I usually write such that so many times I just write S period, T period. So if I do that, that's what that means. Okay. True or false?
False.
False. There exists an x such that for every y, x is greater than 1. So in other words, what we're getting at, how could you, we're saying that x is bigger than every y, right? So they're saying there's an x that's bigger than every other integer. In other words, this statement, another one way of saying it is, there is a biggest integer. That's probably the simplest way to translate this. That's the meaning of this phrase.
That's untrue because that's using the assumption
That's
that
false.
integers are finite.
It's false. So there's biggest integer? No, that's false. There is no biggest integer. There is no x that's bigger than every other integer y. Okay, so that's a false statement. But you see how this is a kind of a more literal translation of these symbols? But wouldn't it be easier to say that to somebody, there's no biggest integer, right? That's these you know, you might go from like here to here and then back to here, but so what's going to be hard is like if you have a sentence like this and you want to rewrite it like in symbolic notation, there is a biggest integer. That means maybe you probably wouldn't think of that off the bat as there exists an x such that for every y, x is greater than y. But that's these mean the same thing. But the meaning behind them is the same.
It'd be true if you switched to quantifiers, wouldn't it? For every
Okay.
x, the y is bigger.
Yeah, that would be true, right? So if we switch the quantifiers, it would say for every y, there exists an x such that x is greater than y. So it's basically saying for
No matter what you pick. You can
yeah, no matter what you pick, you can always find a bigger integer, right? Give me x, I can tell x plus 1, right? So yeah, if I switch the order, then it would be true. Okay. All right, any questions? No questions? Okay, so that finishes 2.7. I'll post all the homework for the week after today. So page 51, number 1 through 6. So if you get stuck, this is where I don't want 1, 3, and 5 to look exactly like the back of the book. I mean, there's many ways you can interpret these sentences, but you're given symbolic logic and actually you translate back to English. Okay, you can start off with your kind of more literal translations. Okay, but just give it a shot. 1 through 6. Okay, if you get stuck, you can try look in the back of the book. Okay, I'm gonna let the camera roll, but let's take a 1 minute break before we start the next section.
Are you still doing that on the record?
Yes. Thanks for clarifying that. Yeah, so all of them, this week is Monday. No. Okay. All right. So let's get back. So 2.8, there's a couple of these, 2 or 3 of these sections at the end of chapter 2 where the author is just trying to reiterate or trying to make this point about the subtleties and logical notation. And they wanted to talk about P implies Q. You could have, we know what an open sentence is. The sentence, you can't say it's a statement because it depends on what the variable is. But when you have an open statement here and an open statement here, you can still consider this to be a statement because it's usually referring to all things in your universe. Okay, so I said when you make these statements over and over and over, you're using the same set. Like we're always talking about integers. We often just drop the integer set if it's understood what the universe is. Okay, so when you say stuff like if x is even, then x squared is even. I mean, what are the types of numbers that you talk about being even? You don't talk about rational numbers being even. You don't talk about complex numbers being even. You talk about integers or natural numbers, okay? So integers, really, you talk about, if x isn't, so really when you say if x is even, then x squared is even, you really mean for every integer x, if x is even, then x squared is even, okay? So we really mean for every integer x, if x is even, then x squared is even, okay? So oftentimes when there's a theorem or a statement we're about to prove that's a conditional P implies Q statement, it's really it's really a universal statement about all elements of your set. So what the author is saying in this section is that just because you don't have this phrase first, we still want to consider if x is even, then x squared is even. We still want to consider that as a statement that we can prove true or false. Okay. And this would be without this quantifier. I would still say this is a true statement because if x is an even integer, then it is true that x squared is even. Okay. And if you're talking about any x that you give, if you plug it in for this x, this will be a true statement. So this is true for all x's. So we still want to consider this a statement. And he even goes so far as to make a definition that if P is an open sentence, if P is an open sentence, Q is an open sentence, then P implies Q is still a statement. Okay. So for example, this we'd say is a true statement. Okay. So if x is a multiple of 6, then x is even. You believe that? Is it true or false? If x is a multiple of 6, then x is even. It actually is true. And again, what they were saying is, this is true for every integer x. I mean, give me an integer, then this is true. Okay, and I'll show you in the next section how you can actually, any if-then statement, you can write it as for every statement, a universally quantified statement, as the book said. If P is prime, then P is odd. True or false? False. Because I can find a number that makes the first statement true, but makes the second statement false. So this if-then statement would be false. Right? 2 is prime, but 2 is not odd. So this would be a false statement. Okay? So even though these are if P then Q, where the P and Q are open statements, it's still, when you combine them as a conditional sentence, we still consider these statements. Okay, so a lot of theorems that you prove are in this form, if-then statements. So he's just pointing this out, that he defines these just to make certain that we still consider these statements. Okay, that's all from 2.8. 2.9, we're going to get back to translating English into symbols. Okay, so in 2.7, for example, the exercises in 2.7 are all symbols, and you had to convert them back to English. Now, 2.9 is focusing on translating English into symbolic logic. Okay, and this stuff takes some getting used to. So here's some phrases. Did I do this one already? Every integer is prime. Every integer is prime. So this is clearly false, right? It's not a true statement, but I'm just providing statements. We're going to practice translating them into symbolic language. So every integer is prime. Okay? What's the translation? On A, talking about integers.
N, element of integers.
Okay? So for every integer n, what about n? N is prime. I remember one thing I meant to say. When he uses this notation, I've never seen this before. Like if he says, instead of saying x is even, if you notice this in the book, he uses this abbreviation, E of x. That's his notation for x is even. So what if I wanted to say x is odd? Did you see what his notation is? O of x, which seems all right to you guys, right? But capital O of x means something completely different. In upper mathematics, I mean, this means that the quantity is, it talks about the relative size asymptotic behavior of the quantity you're talking about. So, I mean, I don't like this notation, I've never seen it. I couldn't find where he officially defined that. But he just started using that, like E of n means n is even. I don't know, I'm not going to use that, but just, if you see that in the book, just note that's what it means. Okay? So, every integer is prime for every n element of the integer, n is prime. Okay. So here's a fact. Every universally quantified statement, okay, for example, this one, so using the universal quantifier, so any statement like this, for every n is prime, okay, you can actually write them as a conditional statement, P implies Q type of statement, okay. Every universally quantified statement can be written as a conditional statement. Okay, so if you have a statement like this, for every integer n is prime. Okay, let me show you how I could write that as a conditional statement. I could say n is an integer implies n is prime. So those two will be both would be correct symbolic notation for the statement every integer is prime. Okay, so anytime you have a for every statement or a universally quantified statement, you can write it like this. For every integer is prime. Okay, so the saying is that if you have an integer, it must be prime. And that's what this statement is saying. So if you have an integer, it implies that the integer is prime. Remember, so these are both false statements, right? I mean, this, no matter how you write it, it's still a false statement. Okay. All right. So how another universally quantified statement? All integers are even. Okay. Clearly another false statement, right? Not all integers are even. But okay, here's the thing: all integers are even. So similar to the first one, you would say something like all integers. So for every n in Z, n is even. Right? How could you rewrite it though as a conditional statement? P implies P type statement. N and Z implies n is even. Okay. So either one would be fine.
Is there a reason why the book presents so many false statements? Wouldn't it be just as easy for him to give us a true statement?
Yeah, I mean, well, like for example, you have to say all integers are even or odd. I mean, you can say that, right? I mean, that's a true statement. How would it change? That's a true statement. Sure. Maybe just make you think. Are these true? So yeah, this was one sentence I saw in the book. X is even, but Y is odd. Okay. So just this example is just to point out that you don't see the word for every. You don't see the word that exists. So this is not a quantified statement. You don't use the quantifiers. But there's this but, this conjunction, but, and that you have to interpret that as an and statement. Okay, so X is even, but Y is odd. You would just say X is even and Y is odd. Okay, so even though you don't see the and word, you have to translate conjunction but as and.
Does she use the there exists word?
Well, I'm not saying anything about
I think we're
the
just
existence of an X or a Y. I'm not saying anything for every So in 2.9, we don't have to have a quantified statement. This could have been in the previous section on and or.
I think we're just trying to assume that for every X there is a Y.
Right, well now you're thinking that way, right, because we're using that today, but just think, I mean, the only point of this example is that the word but you would interpret as and when you use symbols. Here's your quantifier statement here. How about this? So some integers are negative. Integers are negative.
There exists.
Okay. There exists.
In
N,
element
N.
integer
Okay. If there exists an integer n,
such that
n
is less than 0.
I like it. So that's what, being negative means that it's less than 0. Right? Some integers are negative. There exists an integer n such that n is less than 0. So you see how, if you saw this and I said translate it back into English, you could give me a little translation, something like, there exists an n, which is an element of the integer, such that n is less than 0. Now, if you wrote all those words out, that would be correct. But really, the gist of this, what's it trying to say? It's trying to say some integers are negative, right? Some integers are negative. That's a much easier way to read this, translate it. Not all integers are positive. So maybe to do this one, you might want to look at the phrase all integers are positive, and then the not, you just use your negation symbol. Okay. So how would you write all integers are positive? Okay, so all integers, for every integer n, what? N is greater than 0, so I would say all integers are positive. But we're saying not all integers are positive, so you would say, I'll maybe put parentheses around. I'm negating the whole sentence. It is not the case that every integer n is positive or greater than 0. Okay. Not all integers are positive. How could you say not all integers are positive in a different way? How could you, just in English, how could you say not all integers are positive? Some integers are negative. Okay, so you see how you switch from this is used as a for all, and you found a way to say it with using there exists statement. So we'll talk about that more in section 2.10 when we do the negation of a quantified statement. You could actually say, another way to get the same meaning across, you're really saying some integers are not positive, right? That's what I was saying. Not all integers are positive. You're saying, well, some integers are not positive. So some integers are not positive.
So, number 4 is the negation of number 5.
Nope. Close. So I purposely said some integers are not positive. Because what's the opposite of not positive? What is another way to say not positive?
Negative.
It's not negative. 0 is not positive. So if you say something is not positive, instead of saying n is greater than, it's not the case that n is greater than 0. That's not the same as saying n is less than 0. It's the same as saying n is less than or equal to 0. So non-positive is not the same as saying negative. You got to worry about 0. Maybe it'd be better if I start out with not all integers are negative, and saying some integers are non-negative. So being not positive is the same as saying less than or equal to 0. last one. This is all you people that are going to go on and take analysis one day. For every positive number, epsilon, looks like a little, it's like a backwards 3, but it's Greek letter epsilon. So for every positive number, epsilon, there is a positive number, capital M, for which the absolute value of f of x minus b is less than epsilon whenever x is greater than n. So this is the kind of statement you write all the time in an analysis class. This is really calculus. When you guys have taken calculus, you talk about limits, like what's happening to a function as x gets really big, for example. Well, this is the rigor behind those statements that your professor might have made about, well, the function's getting closer to this number m as x gets really big. Well, this is what it means to get really, really close, or to a limit. The absolute value of f of x minus b, that's the distance from f of x to b. So actually, f of x is getting closer and closer to b when x is getting bigger than m, really, really big, usually. Okay. So this is the kind of stuff you see a lot in an analysis class. This is called. There's other things called delta epsilon proofs. You'll have an epsilon. You'll say for every positive number epsilon, there's a positive number delta, and those proofs. There's a ton of those proofs in analysis. Okay. So for every positive number epsilon, for every epsilon greater than 0, that's how you would write that. For every positive number epsilon, it's right. For every epsilon greater than 0, there exists a positive number m. Okay, there exists an m greater than or equal to 0. The next phrase is a conditional phrase, conditional sentence, for which the absolute value of f of x minus b is less than epsilon whenever x is greater than m.
So absolute value of f of x minus b is less than epsilon implies.
Nope. This is q whenever p. So I would write this as x is greater than m implies the absolute value of f of x minus b is less than epsilon. So usually m is going to be a really big number, and you would say, no matter how small you can choose epsilon, I can find an m really big that when x is really even bigger than m, then the distance from f of x to b is going to be really, really small, less than this. Okay? So usually you think of when you do these proofs, epsilon is going to be a really small positive number. Okay? And so in analysis, you'll start out with this all the time. You'll say, let epsilon be greater than 0. And I mean, this is how proofs go. And you just do this all the time in analysis. Let epsilon be greater than 0. Okay? And you write this so many times that I heard that the shortest math joke is let epsilon be less than 0. Ha ha ha! Anybody's had analysis, epsilon's always a small positive number. So this is something when no one understands analysis. All right, so that's all of 2.9. So 2.9, I think 2.9, 2.7 is kind of the same. Really, it should be the same section. It's just one you're translating logic to English, one you're translating English to logic. Okay. So homework due Monday. So 2.9, page 55. Number 1, 2, 3, 4, 5, 9, and 10. And again, you notice a lot of odd number problems there. Usually, like up to this point, I only saw like one odd number problem. So my point is, I want you guys to be looking at how it's okay to look at the back of the book, just try not to copy out, the back of the book. But I want you to think about the problems, think about how you would translate that sentence to symbols. If you really get stuck, take a look at the book, but try to, try to think about it before you go ahead and cheat. Okay. There's no homework for 2.8. So really, today, just 2.7, 2.9. And it's one is symbols to English, the other one is English to symbols. Okay? And half of them are back in the book. Alright, so I think we're in a good place. We'll do, really, there's only one real section I need to cover from chapter 2 for the test. 2.10, which is using negation of quantified systems. So the rest of it is kind of like notes to the students to read the textbook.
Pretty much next quiz is just
Yeah. So we'll have your homework due Monday, and then just up to this 2.9 will be on. We'll have a quiz next Wednesday on that. Okay. So then we will have section 2.10, which we'll have a quiz on. But we still have to have that on the test. The test coming up December 10th. So, maybe, you don't know. You don't know, it could be. So February 10th.
so we have to go back here next year.
Yeah.